I'm Dr. Jeyaseelan. I'm very happy to introduce Professor Shrikant I Bangdiwala, who is currently the Professor of Biostatistics at the McMaster University. He's the statistical chair for at the Population Health Research Institute at McMaster University. He was a Professor of Biostatistics program. He was a Professor of Biostatistics in the University of North Carolina earlier. And after his superannuation, he came over to McMaster University. When he was in the University of North Carolina, he visited CMC since 1996, and he helped us to establish Biostatistics Resource and Training Center and Clinical Data Management Center at the Biostatistics Department at Vellore. He trained us in clinical trial methods and advanced statistical methods like multi-level modeling and so on. That I still remember. In 2003, we had a workshop on multi-level modeling. And now I asked him to do this lecture for you people. Now, the next 2 days, he'll also talk about multi-level modeling. Unfortunately, we do not have time to do the practicals. If needed, we'll arrange practical sessions separately. And that is all I have. Dr. Kant, please start your lecture. Thank you very much.
Okay, so I assume everybody can see my slides properly and can hear me properly. Good evening, everybody. So today is the beginning of a series of 3 lectures on multi-level data models. We'll be talking about multi-level models as well as GEE models. But today we're going to start off with setting up the base so that everybody has a common understanding of some common regression models that we use in health sciences research. So what do we do in health sciences research? We usually are trying to understand some phenomenon in a population. But the key points are that we as statisticians recognize that there is variability in the system, right? The outcome of interest, it varies, the potential factors associated with it vary. So that variability gives rise to uncertainty. We also are never usually studying the entire population. And so by taking just a limited number of people from a population, there's chance in the sampling process, so we have uncertainty in our results due to that. And our models that we're going to be using may not be the proper models. We may not include the proper variables. We may not have the same correct functional form. So we have misspecification that gives rise to uncertainty. And so the final thing that many non-statisticians don't recognize is that you may have exactly the same situations, but chance may determine what you actually observe. So that gives the 4th reason for uncertainty. So the key underlying principle of statistics is that it's the science that allows for understanding of quantitative information in the midst of this uncertainty. And so the uncertainty comes from that inherent variability that I mentioned, but also from the process of we're not able to observe the population of interest. We take a sample, we observe similar things that we are interested in the population in the sample, we call those as statistics. And then through the process of statistical inference, we sort of complete the circle and go back up and make statements, which are probability statements about these parameters. And then, of course, the role of chance that I've mentioned. So what are our research questions in health sciences research? Well, typical research questions we have are descriptive. It's one, how are things distributed? We're estimating characteristics of the distribution. We're looking for factors associated or even causing the phenomenon. So this is the exploratory descriptive parts of our research questions. But the more common research question is somebody makes a claim about the phenomenon. So we're trying to convince somebody that your claim about the distribution characteristics, like the mean is such and such, or associations, is to be believed. And so we want to demonstrate that it's not biased, that it's unlikely to be due to chance, And this is what we call as inferential statistics. You have descriptor statistics, and then you have inferential statistics. But in both of these, we are looking at associations, right? And so this is the key part of regression. And this is why I'm mentioning this. So when we're trying to understand the phenomenon of relationships between variables or associations between variables, we have different types of research questions, okay? And so the next slide I'm going to be talking about, suppose I have only two variables. I have an outcome variable and I have an exposure variable. So we may have a research question that says, is blood pressure associated with body mass index? Both of them are continuous. How could we describe this? Well, we could look at graphically at a scatter plot. How can we summarize the amount of association? Well, we use a correlation measure. We could use Pearson's correlation measure. And how do we look at relationships between them? We could do a simple linear regression. However, we could be asking, is blood pressure associated with obesity? Obesity is now dichotomizing BMI into those people that are above 30. So now we have a continuous variable and a binary variable. So we really, okay, everybody please mute themselves, or if the host or co-host can mute everybody, that would be fantastic. So we cannot do a scatter plot in this situation. So we could do box plots. There is no measure of association really. And we could do, depending on which is the outcome variable, we could do a linear regression or a logistic regression. If we say, is hypertension associated with obesity? Now both of these are binary and there is no plot for this, but we can quantify the amount of association by the odds ratio. And the typical way of looking at the association in regression is with a logistic regression. Finally, we could be asking, is obesity associated with time to becoming hypertensive, for example? So now we have the outcome is a time to event variable. And this, you can have Kaplan-Meier plots, for example, to be descriptive, or a hazard ratio over time to be a way of getting the association, or Cox proportional hazards regression. So we can have these as the measures of association, but we are looking at regression. And I'm going to be basically talking about the two common ones, which are linear regression and logistic regression. I don't think we'll have time to talk about the Cox proportional hazards regression. That's a whole other lecture. Okay, I will briefly mention something about it later on. So moving on, I'm assuming that almost everybody knows what simple linear regression is about. You're looking at a mathematical equation where you have the intercept and the slope, or some people call it the position of the line. And so we have here a study where they were looking at in the police in Austria, we're looking at if I have to take the blood alcohol concentration of drivers from the blood in a sample, they have to go to, have to draw blood from the person, but it's a lot easier to do it from a breathalyzer. Is there an association between the blood alcohol that I get from the breath versus the blood alcohol that I get from a sample? So they took a sample of 59 people and saw that there was a relationship. Yeah, it's a positive relationship as one would expect, but is it a strong positive relationship? So one thing that we could do here is, construct, and I'm presenting results in Stata, but you can do it in any software. So just you can regress the blood alcohol concentration in the breath as predictor of the blood alcohol concentration in the sample, a blood sample. And so what do we get? Well, we can partition the sums of squares, the amount of variability due to the explanation by the breath alcohol out of the total sums of squares. So this is what we normally call the analysis of variance table. So we're decomposing the variability total variability into that due to breath alcohol concentration. And then what is not explained is called the residual. And the R squared is nothing but the square of the correlation coefficient between them. So it's pretty strong correlation. And so we talk about the R squared explaining 75% of the variability in the blood alcohol concentration if I take the breathalyzer. Well, it's not 100%, but it is 75%. So this is simple linear regression. I'm assuming everybody has encountered this already. What are the objectives of regression? Well, the objectives are many, and that's part of the issue here, because regression is not just to do one thing. It can be used for multiple things. And so we usually think about, as I just said, we want to estimate the association of an outcome with, in this case, one or more different independent variables, x's, or understand how big or important is the effect, or predict y from one or more x. So we could be predicting, or we may be estimating it on a specific value of x, controlling for other variables, and look at the relative importance of one or more x's in determining y, and determining the best model for predicting y from one or more x's. So depending on your type of research question, what you focus on after you do the regression is very important. So I want to illustrate the concept of linear regression using data from a well-known study back in the 1980s called MONICA, and that's Monitoring Trends and Determinants in Cardiovascular Disease. It was sponsored by the World Health Organization globally, although predominantly there were many countries in Europe. There were 21 countries in total, over 4 continents, but they were mainly European countries, and looking at rates of hospitalized cardiovascular disease events, case fatality, and so forth. So one of the data sets that I got from them, right, I took a subset of the data, is there's this thousands of data points. So I just took a random sample of the data so that I can illustrate it. And so I had made up a research question. Is your body mass index a good predictor of systolic blood pressure? That is, if you know somebody's body mass index, can you tell something about their systolic blood pressure? That's what we mean by are they associated. And what we see here in the scatter plot, both of these are continuous, so we can do a scatter plot. And we have a fitted, straight, simple linear regression line. And I have here, 337 observations. But interestingly, this line could be slightly different because there's these 2 points here that sort of are maybe pulling the line to not be as steep in the slope as possible. We call these outliers, and we'll talk a little bit about what is the influence that these 2 observations may have on the data. So then what do? Well, we can construct the same simple linear regression, and we observe that even though we had 342 observations, we have 337 in the analysis. Why is that? Because there's people that are missing data. Some of them are missing. There's one person missing BMI and 3 people missing systolic blood pressure, for example. And so we can do this very simply, similar to before. And we focus on this and say, oh, wait a second. R squared is only 16%. So it's pretty small. This is not great to look at this relationship. BMI is not really explaining a lot of the variability in systolic blood pressure. So then the question arises, are there other variables in the data set that may affect the relationship of BMI to systolic blood pressure? And that's the difference between simple and multiple linear regression. So in a simple linear regression, we just have only one predictor. And this is the standard formula where you have this intercept, the slope, and the error term, which is assumed usually to be normal variable. And multiple linear regression is exactly the same functional form, but now I have many more parameters, okay? What changes between simple and multiple linear regression? Well, the ANOVA table, the interpretation is very similar. It's exactly the same in the sense that we are decomposing the total sums of squares, the total variability around the mean of the y's, into that is explained by the regression. Donna Maria, can you please mute yourself? And we have the error sums of squares. Is the amount of variation that is still unexplained after all the x's are included in the model, okay? And we're decomposing the variance. Now, why am I mentioning this decomposing of the variance? You will see that because that's going to be the emphasis of the multi-level models that we talk about tomorrow, okay? But anyway, the standard ANOVA table decomposes the total sums of squares into sum of squares of regression and the sum of squares of error, okay? And we could figure out the degrees of freedom depends on the number of x's that we put in the model. So there are other differences. So the ANOVA table may be the same, but the interpretation of the beta coefficients is not as straightforward. It's not just the effect of x on y or the slope of x on y. There's geometry in higher dimensions now. How we do model goodness of fit is different. And we have lots of choices on which variables to include in the model, okay? Which ones we include, the order in which we include them, and which ones we keep in the final model, okay? Why are these things important? Because the x's may be related to each other. We can have the problem of collinearity, and we're going to talk about collinearity. And x may have a different relationship with y depending on the inclusion of other x's in the model. And we'll talk about this term called confounding, which you may have heard about, as well as mediation. Or an x may have a different relationship with y at different levels of another x. So we call that, the epidemiologists call it effect modification. Statisticians, we call it interaction, okay? And their sociologists call this mediation and this moderation. So there's people come up with different terms for similar concepts. So we're going to have to worry about in multiple linear regression about collinearity, about confounding, and about effect modification, okay? So let's look at it very simple. We'll go from simple linear regression to multiple regression, but only with two predictors. So now the model equation is as simple as this. We just have the intercept and we have the slope for x1 and the slope for x2. How do we interpret these? Beta 0 is the value of the expected value of y, because now we have to deal with the error, which has an expectation of 0. So it's when I take the expected values of the mean value of y when x1 is 0 and x2 is 0, okay? Beta 1 is the value of the expected value of y for a unit change in x1 while x2 is held constant, or we can usually say having adjusted for x2. And beta 2 is the value of the expected value of y for a unit change in x2 while x1 is held constant or having adjusted for x1. So that's the difference, that the coefficients of x1 and of x2 have to always be adjusted. We say they have been adjusted for whatever else is in the model, or while everything else is held constant, okay? And that is a crucial aspect of multiple regression. What is the R squared? The R squared here is not only the percent of variability explained, but is interpreted as sometimes called the coefficient of determination. It's a measure of the overall linear association of y with the set of independent variables, okay? And most people just easily think about it as proportion of the variance of y, of the total variability that's accounted for by the set of independent variables, okay? And every software will give you this. So it's a measure of how good is the model in explaining the variation in Y. So it's the sum of squares of regression over the total sums of squares, which could be broken out as this. Okay. Now, there is also an adjustment to the R squared that is often done when we're doing multiple regression. And that is, every time you add a variable to the model, it's going to explain some of the regression of the Y's sums of squares, but is it worthwhile to do so? So the adjusted R squared is basically taking the R squared and adjusting for how many parameters you have in the model, where the parameters are P, okay? And otherwise, it's just you're paying a little bit of a penalty for having done that, is all there is. So it accounts for the parameters there that you have adjusted for. So it's equivalent if P is equal to 0 if you don't have any parameters. But adjusted R squared increases only if a new variable improves the model more than would be expected by chance. Okay, so if you have over parameterized your model with some more variables that do not reduce the sum of squares of error, you can even get a negative one. So, but it's hard to do so, and it's only useful when comparing models. Okay, and trying to choose the best model that you want to have. So let's go back to the Monica project. And remember, we're looking at, does BMI have anything to do with the average systolic blood pressure? And what happens when we add a new variable? So now I'm going to add the variable smoking to it. What do I look at here? The total sums of squares is going to be the same, 1, 2, 6, 9, 9, 2, right? That doesn't change. The sum of squares of regression, and I add something, usually is going to increase, right? Because that's, you're explaining some of the variability by adding another variable into the model. So therefore, the sum of squares of residual will be slightly lower. The F statistic, which comes from R.A. Fisher, F for Fisher, is a measure of how much of the variability that's explained by the model, is that a significant amount or not? And so we get the F statistic here is, though you want it to be larger, here it doesn't do that much more, okay? Does the R squared improve? Well, it was 0.16 here, which was not good. Smoking doesn't really add much more. It goes to 0.18, okay? Look at the adjusted R squared, was 0.16, and here it's 0.17. So it goes a little bit more here as you're paying the penalty here. Does the coefficient for BMI change? 1.90 to 1.87. So it's not that much different. And so the model equation, model goodness of fit, is not that much different here. Okay. Notice here that the slope, I'm sorry, the intercept has changed a little bit from 79 to 81, etc. But model goodness of fit, which is the better model to fit the data? Is it driven by the R squared only? So model goodness of fit is something that we are interested and concerned about, okay? So R squared assesses the fit in terms of variance explained. So that's why we look at R squared. But we could also look at the beta coefficients and assess the fit in terms of, does it make sense? For every unit increase in systolic blood pressure, do I get this? Is that a meaningful change? Oh, sorry, BMI. Do I get a meaningful change in systolic blood pressure? Does that make clinical sense? Now you go and you talk to a clinician about this. So also we should check the assumptions as a fit in terms of, is the model appropriate or we have misspecified? What are the assumptions? Independent observations, linearity. We're going to see that tomorrow. We don't have what to do when we don't have independent observations. But you have linearity, you have equal variances at different points of X's, and that's what we call homoscedasticity. The errors have normal distributions, and there's no multicollinearity, okay? So these are things we have to check. Okay, so how do we go about checking it? Sachit Ganapati, yes, thank you. Is my independent variable related to other variables that are believed to be associated with the outcome? So now we're saying, is there other variables that could be explaining the variability in the systolic blood pressure, but maybe they are messing up the association of BMI with the blood pressure because they're associated with BMI. So we can look at cholesterol. We see that cholesterol and BMI are strongly associated. The p-value is 0.004. So it is strongly associated. And so then becomes the question, should I include total cholesterol in the model? What will happen if I do so? So I could look at age. Is there a correlation of BMI with age? And there is a slight correlation. It's not that great, it's 0.29. I could do it in years, I could do it in months, it's the same thing. You get the same amount of correlation, it's just the units are different. So remember that the beta 1, the slope is not unitless, it has units. And you can go either do it in months or years, you get the same result. So is the relationship of my independent variable of interest, the BMI, to the dependent variable of systolic blood pressure different depending on levels of another variable? That's what we call interaction. So if the effect of body mass index or the relationship of body mass index to systolic blood pressure is different at different levels of another variable, that is the actual definition of interaction. Okay. So for example, if you smoke, do you have one relationship that's different from if you don't smoke? Well, not that much different, right? What about if you're taking medication for hypertension versus if you do not? If you're taking medication, you have this line, and if you're not, it's there. We see that they're a lot lower, but the slopes are not that much different, okay? So it could be that it's not an interaction. Interaction means that the slopes are different, but there is a effect of taking medication in the sense of lowering your systolic blood pressure, which would make sense. If you're taking medication for hypertension and it works, it should lower your blood pressure. So how do we test this? How do we know if there is an interaction? Well, what we do is what's called stratified analysis. So we do look at the relationship of BMI with systolic blood pressure if you're not taking drugs and if you're taking drugs. And if the interaction is strong, we may want to consider reporting these things separately, okay? And how do we assess whether that interaction is significant or not? This is the stratified analysis, but to test whether it's significant or not, we can formally test it by doing a model where we put in the main effect of drugs and the interaction. We have to generate the interaction variable, which is the product of the BMI with taking or not taking drugs, include that in the model, and then we look at whether that's significant. And we see that it's not significant, so we can discard it and not worry about it, okay? So when we're doing multivariable analysis, we wanted to explore associations or generate hypotheses or test associations, okay? Or to do predictions. But all of these are going to have these issues that we want to deal with, whether it's confounding or interaction or causal associations. So let's look at these complications that we may have. What are the complications we may have if, for example, the outcome variable does not have that normal distribution? It does not behave properly. We may have to transform it. Some people categorize. So that's one thing that one would do as a preliminary step. If the x's are not continuous variables, can't even do a scatter plot. We'll talk about how to do dummy indicator variables. If the x's themselves are correlated among themselves, we'll call that multicollinearity. We'll talk about that. or the X's are measured with error. So we have measurement error models. We won't have the time to talk about it. But what if relationships are complex and nonlinear? And now that goes also beyond what we're going to be talking about. But the interactions, we could look at least the simple and complex interactions. So what happens when predictors are correlated? So suppose I have this situation that I have X1 and X2 are the predictors and Y is my outcome. And in case situation A, we see that these are associated. So the overlap means that there's some association. X1 is associated with X2, X1 is associated with Y, and similarly X2 with Y are associated. Here, they are associated with Y, but they're not associated with each other. So in which case will R squared increase more with the addition of X2? Well, if there is, in this case here, X2 is able to explain more of the variability of Y, but here this was already explained by X1. So, in this case, X2 is going to help more in explaining. So when they are independent of each other, it's likely to explain more of the variability of Y. And in this case, if I had X1 and they're overlapped with X2, when I put X2 in the model, the coefficient of X1 is going to change with the addition of X2. Okay, so the answer for this question is B, and the answer for this question is A. Okay. Now, are BMI and smoking correlated? Well, we could do the plot to say there's slight difference of the BMI, whether you smoke or not smoke. And we could test that they're not really that strongly correlated, but there is some correlation between them. But people that smoke may have a slightly less BMI, for example. So how can I go about testing this, right? And that is, so we saw how we tested the interaction term. There's another test we can do is whether it's worth adding a new variable. And this is a test that's called the partial F test. And this is to test an increase in the sum of squares of regression. So we have the null hypothesis that the conditional value of beta 2 given beta 1 is equal to 0. How is this done? We look at the change in the sum of squares of regression relative to the variability, overall variability, and use a change in that to assess importance of added variables. So the order of adding variables to the model matters because once something is there and you're related to that, it could affect it. And we compare standardized coefficients as a measure of how strongly each predictor variable influences the dependent variable. So the beta is in units of standard deviations. Okay. So the next topic I want to talk about is one that's fairly common, and that is when I have categorical predictors, or I've taken a continuous variable and I've categorized it, how do I go including it and how do I interpret the coefficients for these? Many people call these dummy variables. It's probably a better term is to call them indicator variables because dummy has a negative connotation. So one of the things that we have two categorical variables in the Monica project that I was interested in. One is the level of education, which was non-primary, secondary, and higher, and sex, which was male and female. And in my sample of 342, this is the cross tabulation. So we usually always recode as 0, 1, and we created 4 dummy variables for the 4 category education level. So dummy variable 1, we call it education 1, was 1 if none, and 0 if others, and so forth. Okay. Then how do we do the model? Well, what we usually do is we can put in, now I want to see if education in its 4 dummy variables is related to the average systolic blood pressure. But you note what this says here, that education 1 was omitted because of collinearity. And why is that? Because education 1 plus education 2 plus education 3 plus education 4 will be equal to the intercept. And so the model will not work. And so Stata automatically dropped it for me. And so even though I put all 4 of these, the actual model that I had was with the 2, the 3, and the 4. This is called the reference cell model. And what does that mean? Let's look at the, here we have the constant is 120. And what is education 2's coefficient? It is interpreted as the effect of that level of education different from the reference cell, which was no education. So this is having to go back. The categories were primary, secondary, higher. And so this would be the beta 1 here is what is the average systolic blood pressure high increase if you have somebody from primary education versus no education. And this one is if you have secondary education versus no education. And this is higher education versus no education. So it's always against the reference category. Okay, that's why it's called the reference cell model. Okay, this is the standard method to use dummy variables, which is to just do it with a reference cell and you have these remaining. So if you have 4 categories, you have 3 dummies. You can choose which dummies you want. I did not, and Stata chose it for me. But you could say, I want these to be in. You could put education 1, education 3, and education 4 in the model, but then education 2 becomes the reference, for example. There's another way of doing it, and that is I can put all 4 of this and say, don't put the constant or the intercept in it. And what it does now, the coefficients are different, and the model is different. And the model is called the cell mean model. Why? Because these coefficients are the means of those 4 levels of education. What? Mean average systolic blood pressure in those there. So it's not differences now against a reference, it's just the mean of those 4 groups. It's not a common method to use dummy variables, but I'm just mentioning it to you so you know that. Where does it come from? If you calculate the means in those groups, you see that that's exactly what you get if you did this. So the cell mean model coding approach is not common, as I said. It's usually only used when you want to look at the means and how they may change when you add other variables in the model. So, but most people don't really care about, unless education was one of your important variables to look at the means, you may just keep always doing what most softwares by default will do for you. Okay, so let's go back to the reference cell model, but now I'm going to see I have BMI, which is systolic blood pressure, and now I'm going to adjust for education. So my model will have BMI in it, and now these are the education. 3 out of the 4 dummies are included. How do we interpret these coefficients now? Well, for every unit increase in BMI, your average systolic blood pressure increases 1.68. But what about these? 1.68 after adjusting for education level. And what is education 2? That means that relative to somebody that has no education, if I have a primary education, my average systolic blood pressure is 9 units higher, having adjusted for BMI, and that's it. Okay, so that's the way you would have to go about interpreting it. Another way that is easy to interpret or to understand what's going on is to look at what is happening geometrically. So this is our model that we had in our previous slide. And when someone has no education, the model reduces to this. When they have primary, it's this. When secondary, it's this. When it's higher, it's that. what do we observe? They all have the same intercept. They all have the same portion of BMI. And so this is now, we're adding a constant of beta 2, add in beta 3, and add in beta 4 here. So basically we have parallel lines. So by doing dummy variables, what is happening geometrically is basically this. You have the same slope of the relationship of body mass index with average systolic blood pressure, but you have parallel lines for depending on your educational level. Does education change things much? Not really. I mean, these parallel lines are there, but it's, you know, the blue, red, green, and yellow are all pretty much overlapping. So there's not a huge difference between them. So it doesn't make, the systolic blood pressure doesn't have, it's not affected a lot by education, right? So the big question you're all asking yourselves is, how should I build a multivariable model? Okay, so a multiple linear regression model. How do I go about doing it? Well, we can use statistical metrics, and we'll talk about those. We can use standard approaches that vary by what field you work in. If you work in epidemiology, they do it one way. If you work in behavioral sciences, psychologists do it one way. Social sciences, sociologists do it differently. They all are doing things slightly different in their approaches. Mathematically, statistically, they're the same. Use standard approaches determined by the study design. So the RCT's focus is on the effect of the intervention, for example. So that's what you care about. I like to also argue that an important method to build the model is that it use your common sense. And many people don't like to use their common sense because they are afraid to specify subjective criteria. Some people, though, resort to torturing the data until it confesses to some idea of what the model should show. And I say that's not the way to do it. Others like to do what's called p-hacking until they get publishable significant results. That's also a no, and should not be done. So let's go back to the Monica project. What other variables may affect the relationship of BMI to systolic blood pressure? I chose drugs and smoking, okay, to continue with our example. So how do we incorporate the variables? Well, we can let the software think for us. And those are things that were taught back in the 1970s and 80s. It's, oh yeah, we have computers, let it do the thinking. So we have these routines called stepwise forward and backward. And we even now have the ability to do all possible models. So if you have 20 independent variables, it can look at all possible interactions because we have fast computers now, and it will just see which is the best one. In terms of what? In terms of metrics of what does it explain, right? Or things like that, or significance. You could have that done. I'm not sure that's the best way to do it. We can argue about that. As I said, torturing the data till it confesses to what you want is what many people do. I don't think that's the way to do it. But you should have somehow, you're not doing this without any context. You have some sort of interpretation that makes sense, and that's a contextual clinical interpretation. Now, other issues, are there synergistic effects? That's what interaction is. So the relationship with the outcome is affected by another factor. Or is there a confounding, which means that if the relation of one factor with the outcome is different, whether you consider or not a third factor. And then the issue of collinearity that we mentioned. And let's talk about these issues, okay? Now, before we get there, there are other considerations on variable selection, and there are many approaches, okay? those are ones that focus on model fit, and these are using statistical metrics for it. There are others that focus on model interpretation, on making sense, and the sources of variability. In either case, in all cases, you always should check the model assumptions, right? The linearity, the independence of the observations, and the distributional assumptions. So let's look at how we build models in some common ways. So one of those is Professor David Kleinbaum at Emory University, who says the variable specification or choice should be based on the literature. So you would restrict attention to clinically or biologically meaningful. You just don't dump everything into the model that you have in your data, right? You think about it first. You can add if you think that there may be interaction terms of interest, or you can skip that. But you should consider this confounding assessment. His student, Ray Greenberg, came out with guidelines for how to go about doing this in a joint paper in 1985. And it says that you identify your independent variable of interest as exposure. So use the term exposure for the variable of interest. The outcome of interest is called outcome. And now you want to definitely always include the exposure variable in your model. And then they propose an algorithm or steps to see whether other covariates may be either effect modifiers, which are interaction terms, or confounders. And a confounder can strengthen or weaken a relationship. So for example, if we're looking at the relationship between the exposure of coffee drinking and the outcome of lung cancer, is coffee drinking related to smoking? Possibly. Is smoking causing cancer, lung cancer? Definitely. So smoking is a confounder, for example. So how do we determine if something is a confounder? They propose 3 important criteria. The confounder has to be an independent risk factor for the outcome, either causal or surrogate. So smoking causes lung cancer. The confounder must be associated with the exposure. So smoking and coffee drinking are associated. They don't have to cause each other. They just have to be associated. A confounder cannot be an intermediate variable between the exposures. That smoking is not caused by drinking coffee. That's what an intermediate variable is. Okay. So those determine confounders. What is an effect modifier? So before checking if a variable is a confounder, you should first discard the possibility that it is an effect modifier. And an effect modifier is an interaction term, basically. And that says that the relationship between exposure of coffee drinking and lung cancer is different at different levels of the third variable. So for example, ethnicity, because different people may not have the same relationship between coffee drinking and lung cancer. So how do we do that? That's what we saw before. That was a stratified analysis, and you can do a test of interaction. So graphically, what does this look like? An interaction means that the effect of X on Y, so here's a scatter plot of X on Y, or now here X1 on Y, depends on the level of a third variable, X2. So the relationship here of X on Y, X1 on Y is different at X2 0 versus X2 equals 1. So the slopes are different. That's what it's looking. Okay. Now, this term mediation is another interesting one that has been used, and that is to talk about causal relationships. And confounding, we saw that if you have the exposure has a relationship with Y, and the confounder has a relationship with Y, causes Y, and these are associated, then C is a confounder. A mediation is very similar, except that these arrows go only in one direction, meaning that this causes that. So mediator is one that has a direct and an indirect effect of the X has a direct and an indirect effect on Y. The direct one is this one, and the indirect one is through the mediator. Okay. Interestingly, how you determine this is basically exactly the same way. Whether it's a confounder or a mediator is assessed the same way. You fit two models. You fit a model with and without the potential confounder or mediator, and look at the effect on the slopes of X, right, of your exposure variable. And if they're different, then it is a confounder or it's a mediator. In mediation analysis, they actually calculate what is the direct effect and what is the indirect effect. Okay. Now, so people say you should use knowledge on this to build your association models, and I tend to agree with that. However, you want to avoid under-adjustment, which is you're not including some relevant confounders, or over-adjustment, which causes bias and or imprecision. So if we can consistently estimate the total causal effect of X by ignoring M, then by adding M, distorts the estimation of causal effects. So that's one thing just to consider. And this is a recent paper, or maybe 10 years ago now, that if you do over-adjustment in epidemiologic studies, you may get some bias in it. Okay, going back to our Monica project, the relationship between BMI and systolic blood pressure. We have two potential confounders, smoking and hypertension medication. We check if the interaction is meaningful. We then check if the interaction is significant, and we can decide, no, the interactions are not significant. We can ignore the presence of interaction. It can be attributed to chance. So next we check, is it confounding? So we run two models. This is with and without smoking, and the coefficient of BMI changes less than 10% from 1.86 to 1.90. No big deal. Smoking is not a confounder. No worries. Doesn't have to be in the model. I do it with drugs and with and without drugs, and the coefficient is 1.43 with drugs and 1.9. So there's a big difference. So hypertension medication use is a confounder. I need to keep it in the model as a main effect. Okay, so that's how you do it. So that's the confounding part. Next topic is collinearity. What is collinearity? Well, basically, collinearity is correlation among the independent variables in your model. So geometrically, when we're doing a model, when we have X1, X2, and our outcome is Y, this angle here is 90%. That's what independence means, is that 90% here. If there's correlation, this angle theta becomes smaller. And when it becomes smaller, then there is some correlation. If it's perfect correlation, this theta is equal to 0. And if X1 and X2 is equal to 0, when we're fitting this plane, which is what multiple linear regression is for two independent variables, it's a plane in third dimension. That plane cannot sit on a line and it doesn't know where to be. We have what's called a non-identifiability problem, and that's perfect collinearity. Now, we never usually have perfect collinearity. We have some collinearity. And the consequences of collinearity is that the interpretation of regression coefficient is when, usually is when you hold all of the other independent variables constant, but that correlation affects it. So it becomes difficult for the model to estimate the relationship independently because they tend to change in unison. So coefficient estimates swing wildly. So you can empirically determine collinearity by, if you put a variable in the model, those things change a lot, right? It reduces the precision of the estimate coefficients, which weakens statistical power. So what do? Well, we calculate the variance inflation factor. It's a measure of how correlated is an independent variable with the other variables in the model, not just with one, but with all the other ones, okay? And if it's, equal to 1, there's no correlation, but there's always some. But we tolerate it up to 5. After more than that, then we have to worry about, let's, remove some variables, or let's summarize them, collapse them so that there is no collinearity, right? Another way to do it is called a condition index, which is now working with the correlation among the observation correlation matrix of these variables, and it's harder to calculate, but many softwares do it. And if you get a condition index greater than 10 or so, people worry about it. Okay, so that's collinearity. Now, when you're building model, we have different criteria. You can either want a parsimonious, very few variables, easy, simple one, or you want to include everything. And these are tugging at each other, right? We can do it focusing on goodness of fit, characteristics. So we could focus on variance explained, significance tested, or epidemiologically understand the effect of the exposure, okay, or confirm theories contextually. And what we want to do when we're doing different models is to compare them. And there's multiple ways to say which model is better or not from a metric standpoint, right? So you could look at partial F test, likelihood ratio tests, information criteria are different ways of doing it. The preferred way is the likelihood ratio test, and I'll show that to you in a second. You may have to adjust for multiple testing, but always remember that all of these models are based on your quality of your data, okay? And so you must verify the assumptions. So going back to the Monica project, now I've included the BMI and systolic blood pressure. I've added sex, smoking, and age, okay? And I get this model, and it fits the model using least squares. If I had done it with Stata with GLM, it fits it using maximum likelihood, and I get the same result. There's no difference for continuous normal variables, okay? But I can calculate then the log likelihood if I do it with the GLM. So the model gives me the log likelihood for this model, and that's an explanation of the, how much of the variability is accounted for there. The probability of what I've observed, not variability, sorry, the probability of what I've observed is accounted for. So now I do a model without sex and smoke, and I get a different log likelihood. So I had here 1355, and here's 1356, okay? You want the likelihood to be higher, so smaller negative, okay? And so what the log likelihood, likelihood ratio test statistic is the difference in the log likelihoods multiplied by -2. That is a chi-squared, follows a chi-square distribution with Q degrees of freedom, where Q is the number of different variables that in the two models, or parameters in the model. So here's one for sex and one for smoke. So I can do that, and I do the calculation, and the p-value is 0.16. What does that mean? That means that adding sex and smoke to the model did not really contribute much. So I don't really need to put those in the model. Okay, so I can be fine with BMI and age. Okay, we have lots of topics to cover. We only have half an hour left. So outliers and influential observations are important. We have to worry about these affecting the result. How do we detect it? By those scatter plots, etc., or look at your residuals after you do your regression. We can also calculate, and many softwares do it, the leverage, which is a measure of the extremeness of the observation with respect to the mean of the independent variables. Takes on values from 0 to 1, and you just scrutinize all points with certain high leverages, and then decide yourself whether you want to remove them or not. But you should always be transparent if you do so. Influence could be thought of as the product of leverage and how far it is. Removing the observation substantially changes the estimate. So there is this thing called the measure of distance given by Cook or Cook's distance measures the change in regression coefficients if a particular observation is deleted. And so you scrutinize all the points that have influences that are greater than 1. Okay, Cook's distance is greater than 1. So that's a whirlwind review of multiple linear regression. Now, what happens if I have a discrete outcome or a binary outcome? Everything on multiple linear regression is when the outcome is continuous, and we usually assume that it has the errors have a normal distribution. What happens with a discrete outcome? So now we're looking at the same research type question, right? Of the relationship of that outcome to several predictor variables. Now, if it's discrete binary, like died, not died, or whatever, or I've taken BMI and I've, whether it's less than 25 or greater than 25, overweight or not, note that the outcome is assessed over the same time period in all subjects. So you have same exposure and opportunity to have or develop the outcome. Then we have a different type of regression model. So let's look at a different example. This is a study in the New England Journal on sepsis in 455 patients, where they were actually basically trying to, your temperature goes up with this infection, it's a blood infection, and they were looking at an intervention of giving ibuprofen, and they measured the temperature at different time points in persons. And we have, as the primary question, is the intervention effective against death? Well, given aspirin is not the thing to prevent death, but they had a secondary question. What is the relationship of the acute physiology and chronic health evaluation score, or the Apache score, with 30-day mortality? So the secondary question is the one that I want to focus on, and that is, what is the relationship of the Apache score with mortality? So the Apache score goes from 0 to 40. It is slightly skewed, but you could think of it as normal. And so this is the predictor, the Apache score. What is the outcome, whether you died or not? So one is continuous, one is binary. If I try to do a scatter plot, I get nonsense. I get this. So it's not useful, right? Because here's the Apache scores, and you either have 0 or you have 1. So this is a nonsense thing. What do? Well, I could do box plots. And so I have the distribution of Apache score in those people that were alive and versus those that were dead. It makes sense. People that have higher Apache scores, so the dead people, have higher Apache scores in general than the people that are alive. But there is quite a bit of overlap here, right? So I could fit a lowest line, or I could fit a linear line. A linear line makes absolutely no sense. It looks like that. The lowest line also makes not really much sense because the points are here, right? And neither one of these is satisfactory because there is no way that a line goes through this, right? So what do? Well, we are interested in the probability of death given your Apache score, right? So probability of y equals 1 given x being the Apache score. And here is the assumption. The assumption is that that probability follows the logistic function. And the logistic function is given by the exponential of a linear function of the x over 1 plus the exponential of the linear function of the x. Why do we do this logistic function? Actually, because it adjusts better than a line to the smoothed observations, not to the actual observations, but to the smoothed observations. So here's what I did. I remember I had this, these are the actual points, are the blue ones, but the smoothed points are the lowest ones here, and that's the green smoothed one. This is the linear fit is there, okay? And I get from having, I fit a logistic model to it, and I got the probability that it predicts, what it's probability that it predicts between 0 and 1 for different values of Apache, and that's the orange points here. And you see how the orange points follow this here. So what is going on geometrically? The reason that we're doing this is that our regression equation needs to lie between 0 and 1. Why? Because that's what the outcome lies between. You don't want a probability of dying greater than 1 or less than 0. And the effects of the covariance can be interpreted on a multiplicative scale. So regular linear models are unbounded, from -infinity to infinity. And we want our predictors to be bounded between 0 and 1. And so we could do it like this, where you have a straight line around some range here, and then bound here and go like that. But nobody likes these sharp boundaries and discontinuities here. So this is what the logistic function does. It sort of smooths it out into the sigmoid kind of relationship. And that's why we get that fit. And that's why we use the logistic regression for binary outcomes, okay? So what is it? The probability of the event now is a logistic function like that. This is the parametric assumption of a logistic probability model. We can calculate the odds of event, which is the probability that you're died versus that you don't die. And so if you calculate this, it turns out to be e to this linear function. And so the log odds of the event are the natural log of the odds, and it's linear. So by taking the log odds, we have linearized this. People call this the logit function. So now we can fit a linear model because we've linearized a non-linear function, okay? Now, what is interpretation? The log odds for x and for a value at x and for x plus 1 are given by this. So it's just, if I have a value of x, that's the log odds. If I have a value of x plus 1, that's the log odds, okay? The difference in log odds is what? Well, it's just simply the difference between these two. Nothing unusual between these two, right? That's the difference in the log odds. And I calculate this difference, okay? And if I now get that difference, it turns out to be beta. And beta, and the difference of the logs is just the ratio of the logs, okay? And so if I now take e to the beta, this log disappears, and what do I get? I get this. What is that? That's the odds ratio associated with a unit increase in x. Aha, that's the odds ratio that we want. And interpretation of the logistic regression beta coefficient is always done in terms of the odds ratio, okay? And this is why it is something that clinicians and epidemiologists like to do. So if we go back to our sepsis example now, and this is the mortality status by treatment, the OR was 0.9, and if I do a logistic regression, I get OR of 0.90. So nothing important here in that case. Now, the logistic regression models what? The outcome is a binary or dichotomous variable. There's a linear relationship between the logit and each predictor variable. And remember now, everything that we discussed about multiple linear regression, of multicollinearity, of influential values, of confounding, of interaction, all of that carries forward here, okay? The only thing that's different is the distributional function and the interpretation of the coefficients, okay? But all of those issues of building models and everything, that carries here. So let's think about a multiple logistic regression. What does that do? That means now we don't usually call it multiple logistic regression. We just call it logistic regression. But we have multivariable, I guess, we have multiple independent variables. And just like we had the interpretation of the coefficients are different, here it's the e to the beta 0, or the intercept, is the odds of outcome when all the x's are 0. But e to any one of these is the adjusted odds of outcome for a 1 unit change in that variable when the others are held constant. That's the usual interpretation when you have multiple independent variables, right? Now, when x is continuous, you can calculate the adjusted odds for a k unit change by just multiplying the beta coefficient by k before you exponentiate it. So let's look at the secondary question of the Apache and fate. What is the odds ratio? 1.12, highly significant. What does that mean? That for every unit increase in Apache, your odds of dying increase 12%. Okay. If you do it with the command logistic, you get the odds ratio. If you do it with the command logit, you get it's the coefficients. You'd have to exponentiate this, but significance doesn't change. So if I wanted to say the odds of death increase 12% for every unit increase, but what about for every 5 unit increase in Apache? The odds of death, I multiply 5 times the coefficient before I exponentiate, and now it increases 78%. Okay. Now, this is actually a randomized controlled trial where they had intervention so that the exposure treatment should be in the model. Cannot ignore that in an RCT. So maybe Apache is not the independent variable. Apache could be a confounder, could be an effect modifier. So is Apache, so now we have treatment and fate, okay? And is Apache an effect modifier of the effect of treatment? So I have to have Apache in the model and treatment in the model. And now I have constructed the interaction of treatment and Apache, and I put that, and I see that, oh, no, the interaction is not, so it's not an effect modifier, not an interaction. So then I discarded that. Now I go to see, is it a confounder of the effect? So now I have to put 2 models, one without Apache, and just have treatment and fate, and one with Apache, and see if the odds ratio changes dramatically or not. 0.91, 0.87, not really, okay? So we don't worry about it. So maybe, but maybe you still want to include it. It changes somewhat, so you may want to include it or not include it because itself is significant. It doesn't change it much, but it itself is significant here, right? So you may want to include it in the model. So what's the final model? Well, we also considered maybe we should add the temperature at which these people with sepsis arrived at the ICU. And is that significant? Well, it's actually very significant as well. Okay. And so this is how you build the model very similarly as you do in the other one. But the difference is because this is not normally distributed, the measures of goodness of fit and is slightly different as well as interpretation. So how do we assess goodness of fit? Well, the interpretation I said is adjusted odds ratios. We can do significance of the variables using the wall test, score test, or the likelihood ratio test. We'll talk a little bit more about this, what those look like here. And then we have the metrics of goodness of fit, like paralleling or similar to the others. So multiple logistic regression, the variable selection, all of that stuff is similar. Issues to worry about of interactions, influential observations, errors, collinearity, all of those remain similar to multiple linear regression. But let's look at how do we get a better model? How do we test it? So I have treatment, fate, and Apache, but I have now considered race, their oxygen level, and the temperature when they came in. So I have race and oxygen, and these are not significant. I could look at individually which variables are significant. We see that treatment was not significant, but this is a trial, and it doesn't make sense to not include treatment despite it not being significant. These other things, Apache and temperature, are significant. But how do we know if the model is a good one? Well, there's this pseudo R-squared here that's given. And somebody came up with this, and it's actually not very meaningful, and a lot of people have criticized it. I don't like to use it, so I never look at it. What do I do? Well, since the beta parameters are estimated using maximum likelihood, and they're interpreted as odds ratios, I can look at different test procedures, and I look at measures of predictive ability and goodness of fit statistics, and we'll talk about these in information criteria. So significance testing is these walled chi-squared statistics that test the significance of individual coefficients in the model. And it's just taking the coefficient divided by its standard error squared. It's a chi-squared with 1 degree of freedom. It's very easy to calculate. All the softwares give it to it. But beware, if the estimate of the coefficient is large, then the standard error tends to be inflated and things don't work very well. So I don't like the walled, even though it gives it to you. There's this thing called the score statistic by Lagrange, and it's to see if the expected change in the chi-square statistic is significant when a set of variables is added. It is a test for omitted variables. Sometimes some software gives it to you, but I actually prefer the likelihood ratio test statistic. And that is one where you test one model better than another model by including more variables and now comparing, just like we did with multiple linear regression, doing it now in logistic regression. It requires fitting two models, and that's why people don't like to do it. They want to be lazy and not do it. How are these things related? Actually, they are related. The wall test is looking at the difference of the estimate from beta 0. The likelihood ratio test is looking at, on the scale of beta, this change here from the score test of the beta and beta 0, and the difference in likelihood or log likelihood over here between those two. So this paper actually describes the relationship between the three different tests. So how do I test it? Well, I look at treatment in Apache, and these are related to the wall statistics, because the wall statistics is a chi-squared with 1 degree of freedom, and the z is just the square root of it. So that's how we could look at those if we wanted to. But the best thing is that likelihood ratio. So I fit one with treatment in Apache, we decided, but now I have added race and temperature 0. And the difference in log likelihoods is multiplied by -2, it's 4.77. And it's marginally significant. So you can decide to keep it or not keep it, it's up to you. Measures of predictive ability is this coefficient of discrimination. I don't like the pseudo R-squared, so I'm not talking about it. Yours coefficient of discrimination, and the difference in the average of the event probabilities between the groups when observed events and non-events. And then the diagnostic criteria is very commonly used. So I'll talk about these two. Here's an example of how we would do it with Jur's test of discrimination. You'd have to first get the predicted probabilities and then compare the distribution of predicted probabilities in one group and the other. And in this case, there seemed to be a difference. So it's a benefit to have done this with from that model. So you say this is a good model. And you could compare models by the value of the test of discrimination. So this is how you get the predicted probabilities given the values of X, and you calculate. So the other thing you could do is you can now not only compare this distribution with yours, but you could, once you get the predicted probabilities, you then choose different thresholds for prediction of dead or alive, like 0.3, 0.4, 0.5. because there is an overlap and you don't know, there is not a clear distinction between them. And you see what you get. You get construct tables of 2 by 2. You don't have to do it manually. Computers do it for you. And you can calculate the sensitivity and specificity. You can see that as the cut points move from 0.3, 0.4, 0.5, the sensitivity goes down, but the specificity goes up. And when you plot the sensitivity against 1 minus the specificity, you get what's called the receiver operating characteristic curve. And this diagonal line is a 45-degree angle, is where it's the prediction of the model is just like tossing a coin. So if you have a ROC curve that goes above it, that's good. And the area under the ROC curve, or the AUC, is now a measure of the model's ability to discriminate between cases and controls. And so what we end up doing is doing the model with treatment only. We see that its AUC is basically garbage, 0.51. But when I put Apache, it gets a little bit better. And when I add temperature to the Apache, it gets slightly better. It doesn't add that much more, but the Apache really does explain a lot. So goodness of fit statistics, then we also have deviance and Pearson chi-square statistics, and the Hospital-Lemeshow tests are very common. And we have information criteria. What are these doing? So the Hospital-Lemeshow test is not great since its p-value is close to being significant in this case. And the information criteria by themselves are not meaningful. They only use to compare between models, but the lower the information criteria, the better. So we're almost running out of time. So I just wanted to summarize and say, when do you use logistic regression? When the dependent variable is a binary 0-1 variable that is observed, measured once in a given time period and in different study designs. And model building is the same as for all models and so forth. I don't want to go through all of this because we don't have time, but basically it wanted to, we will be given the slides. The model building is a art, I think, and all statisticians art is how you build it is really very different for different people. George Box, who's a famous statistician, said that all models are wrong, but some are useful. Okay. And so I want to leave you with one final thought, and that is, remember, we're studying relationships. And those relationships depend on the study design, but they all require independent, identically distributed observations. But not all the times do we have independent observations. They can be correlated given sampling or taken repeated measures, and we get hierarchical study designs, correlated data. How do we deal with correlated data? That's tomorrow and Friday. I'll stop there. We have 4 minutes left. Thank you very much. Now, I know I've gone very fast and I've covered an enormous amount of material. So if you have questions, I unfortunately have a seminar in 4 minutes because it's 8 o'clock here. So I will not be able to stay beyond 4 minutes from now, but I'll be happy to, if you get them to Professor Jeyaseelan, he can email them to me and I will be happy to answer them during the course of the day. So while you're sleeping, I'll answer your questions and you can get them tomorrow morning. So, but if there's any burning questions now, let me know. Thanks.
Do we also need to adjust for colliders in addition to the confounders?
What was the adjust for what? Colliders?
Colliders, which are the common effects of X and Y. Confounders are the common causes of X and Y, but colliders are the common effects of X and Y. So do we also, do we need to adjust for colliders in a model? Or
I'm still not understanding your question. You say that confounders are the common
causes of X and Y.
Causes of X. X is an independent variable. We're not talking about.
Yeah.
So I think I'm misunderstanding your question.
So for example,
Give me an example, yeah.
yeah, there was a study which found that smoking mothers had low birth weight babies, but also they were living longer than low birth weight babies who were born to non-smoking mothers. So it was found to be, there was found to be a collider actually there. So this actually low birth weight is, sorry, I'm lost in between, but collider is something which causes both, which is due to both X and Y, both the independent and the dependent variables.
Mr. Dr. Ravi Basu, can you please type it out and send the question? So we'll look at it later on. Okay,
Yeah,
Mr.
because
Shankar.
Yeah.
I have not heard the term collider before. So if you can also give a reference to it, it would be good, because it's not a common term.
Yeah.
Sure,
Shankar?
sure.
Yeah. I have sent through the message also. I just want to know what is can it be possible to, Professor, to apply this BIF test, variance inflation factor test, for those variables which are all categorical in one case, or if there is a mixing of the variables, categoricals plus continuous variables, independent variables, in that case, can we apply BIF?
So VIF usually requires continuous variables, and so that's one of the problems with it. So you may have to use a condition index in that case.
And one more quickly, while interpreting the odds ratio, interpreting the odds ratio in the case of when the odds ratio is greater than 1, is it sensible to interpret in terms of percentage rather than interpreting them in terms of the multiple of that odds quantity?
Yeah, so this is a common problem, and that so if it's greater than 1, and between 1 and 2, that's when people tend to use the percentages. But you are correct that the better way to do it is always in times, as a product. So you could say it is 1.29 times higher odds than such and such.
Yeah,
so that's a preferred way to do it. I agree.
Yeah, thank you, Professor. But in the case of less than 1, it would be in terms of percentage. But in your slide now,
no, if it's less than 1, it's not in terms of percentages. If it's less than 1, it is actually better to recode, because it's just changing the 0 to 1 and 1 to 0. When you recode it, it'll now be in terms of greater than 1. So it's better to do it that way. The percentages, people take a subtraction, and the subtraction from 1 is not correct if it's less than 1.
Can it be possible to, like, suppose odds ratio is 0.9, then we can say that with respect to the reference category, it is the risk is less than this 9% less than the another reference group? Can it be possible to say?
So let me give you an example. If you have an odds ratio of 0.5, do you say it's 50% less, or do you say it's
no, it is not 50. It is not 50. Yes, 50%, 0.5, 50% less in males as compared to the females, like that. Just for instance.
No, so you should say you think about it, it's 2 times more in females than in males, as opposed to 50% less in one than the other.
Okay. Thank you, Professor. Okay. Thank you so much.
Indu, last question, Dr. Indu.
Thank you for the excellent class, sir. My doubt is regarding when you create dummy variables for each level, is it that for primary education, you say those with primary education versus no education, or versus all the others? That is my doubt. For each level, how do you create?
No, because it would say that one is the primary against the none, having adjusted for the other variables of the model, which is having held constant the other educations as well. So it's adjusting for the other ones, but the comparison is against the reference one.
Okay, so whatever the reference variable is, based on that, you say primary education versus the reference variable. high school versus reference variable like that. Okay. Sir.
Yeah.
Thank you.
And
A
thanks,
reference
Khan.
category.
Yeah.
Okay.
Yeah. Thanks,
So
Khan. We are
unfortunately,
running
I have
out
to
now.
go. Okay, so
Okay.
we'll see you
Thank
tomorrow.
you very
Send me the email with the questions.
Okay. Thank you very much. Okay.
Okay.
Thanks for the nice presentation. Thank you very much.